hello. Welcome to section number 3. Thank you all for coming. So some top of the morning announcements for the afternoon. First of all, attendance QR code here. In the attendance QR code survey, there's a little pop quiz on a functional group question. So did you study your functional groups? And then the optional question, which I encourage you to respond to, is what's the song of the summer? What's your song of the summer? If you submit an entry for the song of the summer, I'm going to make a Spotify playlist and send it out to the people who submitted songs of the summer. So please do so. Several kind of announcement things. One, I want to give you a heads up that tonight on Canvas, I will be sending out an announcement that straight up is scary. I'm so sorry. It's going to be about some exam logistics and the practice exams, but it does contain the phrase, if you don't do this, well, you might as well drop the class now. Not mine. I'm quoting Logan from past years, and I'm contextualizing it and being while this is a little bit harsh, the sentiment, there should be some energy, but it's scary. I don't mean for it to be scary. It's coming from a place of love and care. But just be warned, that's going to be coming out tonight. It'll also have some logistics about tomorrow in terms of the rooms for things and practice exams and problem set 1, all this. So that'll be coming out tonight. Tomorrow in lecture, we will be handing out printed versions of the practice exams. So there are 2 practice exams. We're going to give you printed versions. Please take the printed versions and work the printed exams because your exam is going to be on paper for the real exam. So I would highly recommend taking those and working on them. But when you receive them, don't even open them until you're done with PSET 2. PSET 2 should be your number 1 priority in terms of finishing content stuff for this week before getting full into exam studying mode. Okay, so other announcements. Thursday, tomorrow, is a busy day. She's a busy girl. We have lecture, 8:30 to 11:30. Then if you have Thursday lab, you have a lab, 1 to 5. And then there's section in the evening. Now, if you are in Tuesday lab, you're already done with your lab for the week, and you do not have another conflict, please come to the 4:30 one, because otherwise the 6:30 one's going to be too big, and we're going to have more students than seats in the room. So I would appreciate if you can, but if you have a conflict, come to what you can. It's going to be recorded like all the sections, so no worries if you can't make it. But also I think it's better to rip off the Band-Aid rather than to have a section video to watch looming over you over the weekend. Logan's comment of don't travel, shelter in place. A bit much, but just the exams next week. Do what you need to do, but also enjoy yourselves, and you've already done things. What? Next Thursday. Quiz. So remember, the lecture 3 quiz is due tonight. There were several instances of people missing the quiz deadline last week, and we gave an extra attempt. We will probably not be doing that going forward. So please make sure you get the quiz done for tonight. And then the last thing was just lecture 3 is very much let's drink water from the fire hydrant. It's a very overwhelming thing, and I could see in your eyes at some point the lights were on but no one was home. It was just, I'm moving my pen across the page, whatever you say, sir. And it's just because it's so much new information in such a short amount of time in a 3-hour lecture. No one wants to do 3-hour lectures. Logan doesn't want to give a 3-hour lecture. We don't want to attend it. It's what Harvard Summer School makes us do if we were going to offer this in the summer. So it is what it is. But the goal of today's section is to kind of pick up the shattered pieces of lecture 3 from yesterday. And the first half of it or so is really going to be focused on how do we study reactions. Because lecture 3, most all of it was, we taught you 8 or 9 reactions. And it's going to be a really important skill going forward in organic chemistry, so that's why we're spending some time about it. So my TED Talk is how to study reactions, and there are going to be 3 parts over the course of the summer, sprinkled in other sections where we kind of revisit it as it gets a little bit more complicated. But we're going to spend about half a section on the how to study reactions, and then the other half we're going to talk about some of the reaction families from lecture yesterday. So any kind of big logistic questions before we jump into things? Or small logistic questions? Or medium-sized logistic questions? Groovy. Okay, so let's talk about it. The first kind of big idea here is to focus your studying for reactions, you need to know how you're going to be tested on this material. So Logan mentioned this briefly in lecture, but let's talk about what is a line reaction. So a line reaction has three big parts. The first part is we have some sort of starting molecule on the left. We have an arrow, and for this we put any other reagents, any reaction conditions, solvents, and then we have a product molecule on the right. We call it a line reaction because it all essentially fits on line. And when we teach you a reaction in lecture, we will give you a line reaction, and then you'll do like curved arrow stuff below and talk about the mechanism. Okay, so how do we turn line reactions into exam questions? It's very, very easy. We call them box problems because we literally just put a box over one of them. Like literally when I made this in ChemDraw, the typesetting software, I just put the box over the molecule. It's still there, but it's a great way to make a question out of a line reaction. So in this one, we give you starting material and some reagents, and we say draw the product. In this one, we say, okay, here's starting material and product. What are the reagents that get there? And then the harder one is we give you the reagents and the product, and we ask for the starting material. So we're asking you about the same pieces of information, but from various different viewpoints and vantage points. And that's kind of, I think, the trickier thing, or the thing that you have to practice thinking about. One of the 9 pages of your exam will be box problems. I think you'll have like 4 box problems on a page. Now, 9 questions, 90-minute exam, about 10 minutes a page, right? Do you think, for your box problem pages, that you should be writing out full curved arrow mechanisms for all of these? Do you think you would have enough time to do that? No. So let's flag that for later when we talk about like studying reactions. We're going to need a faster way to just straight up write the product without having to think through each curved arrow, each step. And so that is something that we have to incorporate into our studying in order to be able to answer box problems. Okay, so the second type of question that we'll see are mechanism questions. We want the arrows. All of them. So this is the most detailed question that we can ask you about a reaction. We want the full curved arrow mechanism. We can ask about specific HOMO-LUMO, donor-acceptor interactions. And typically the flavor of mechanism question comes in 2 kinds. So we have known mechanism questions. These are straight up like regurgitating the curved arrows from lecture. Like you have directly drawn these arrows on these functional groups before. It is just now on the exam. And there are only a few things that we can do to make it harder than like basic copying of like what the lecture notes are. So one thing that we can do to make it a little bit more complicated is we can stack multiple reactions. So like this curved arrow, or this line reaction here, it has a, I'm blanking, thiolate addition, followed by a Grignard reaction. So we're doing 2 of them. And it's not that it's like one hard reaction, it's just longer. So that's one way that we can make it harder, by doing multiple in a row. Another way we could make it harder is like make you do a reverse reaction of one of the reversible ones. We could start like at an intermediate in the middle, something like that. Other things that we could do to make a known mechanism harder is it's the exact same functional groups, exact same arrows and everything you would expect, but somehow it forms a ring. And then, like, it just makes it visually look weird. It makes it harder to pattern match. But, again, all of the curved arrows should be exactly as they appeared in lecture. The second flavor of mechanism question is a new mechanism. And for this, don't freak out too much about it. We're not going to just, like, throw you to the wolves. It is going to have to be a reaction that is very similar to something you have seen before. Otherwise, it's not a fair question. So, it is going to be, I would say, 90% the same as a reaction that you have seen and been taught directly in the class, but maybe with one tricky step. And you're going to see an example of that on the problem set 2. There's a challenge problem that's one of these kind of new mechanism questions. But we could even do things for a new mechanism question of, we could say directly that this reacts similarly to a carbonyl with whatever. Like, we could tell you directly that, or we could ask you to kind of infer based on some pattern matching of like, which reaction does this look similar to? What functional group does this look similar to? Again, it won't be kind of thrown to the wolves, but one of the 9 pages will be a mechanism question. Last type of question that we can ask you is the hardest type of question that you will be asked in this course. And actually, to be so honest, I think it's the hardest type of question you will be asked in the pre-med curriculum. And that's synthesis questions. This is the thing of, if you're a Harvard College student, I'm so sorry. They don't do this in fall 17. It's only in S17 and in Chem 20 for the chemistry majors. So this is a skill that if you had done it during the year, you wouldn't have to do. But they do a lot more intense MO theory. So it's kind of like a trade-off. We're not going to be doing as crazy MO diagrams. But a synthesis question, what we give you is we give you a starting material and a product, and we say, in 10 or fewer reactions, form the product from the starting material. So let's talk about it. So have y'all ever seen like the hierarchy of learning, which like the lowest level is like remembering, then understanding, then like analyzing, evaluating, explaining, and then the highest level of learning, create or synthesize. So this really is making you internalize this information in such a way that you can create things with it. And so if you are just in the weeds of curved arrows, you're not going to be able to get the big picture enough to do a synthesis question. And so when we are studying reactions, we have to specifically keep an eye towards, how do we study for synthesis? How do we think about this reaction in the context of all the reactions that we are learning, and like what we might want to use it for to build certain molecules. So again, I throw this out here so you know the ways that you are going to be tested on reactions. Our box problems, our mechanisms, and our synthesis. For the first exam, this is too hard for the first exam. This is a second exam synthesis. Your first exam, the synthesis question is only going to have like 6 or 7 steps max, whereas exam 2 will be 10 to 12 steps. Yes. This is also, again, this is think of it as fun puzzles. And you're going to get some practice with this. The eye flare up. You're going to get some practice of this. So you are going to have a synthesis question on exam 2. You're going to have a synthesis practice on each of the practice exams. So you will see it. I'll do some in the exam review as well, yeah.
I was going to ask if it's the same questions for like the group part, but yes.
Yes, it's the exact same exam. Yeah. Was there a question over here? Okay. Yeah. When is the exam? It's next. Oh, it's going to be on Monday and Wednesday next week. It's on the course schedule, but it's going to be in the scary announcement. I'll have details about that. Okay. So the other thing, for synthesis, do not draw curved arrows. We cannot grade that. The things that get you points on the synthesis are reagents on a line and structures. And like we can give a lot of partial credit for that if you like follow a path and like create a molecule that is towards the product. I love giving partial credit on synthesis. If there are curved arrows, that is nothing I can give credit for, because the only thing that earn points are structures and reagents. This is also the one where, do you think, I just said don't draw the curved arrows. So like we need to have that line reaction level of just being able to draw a product without having to think through all the curved arrows of the mechanism. So those are the ideas that are in the head. Now, before we go on to the actual study method, I do want to just give some general advice. So one thing I'm guilty of as a student, because I still like take classes all the time, I like studying that makes me feel good. I like studying that makes me feel smart, where I get to create like little color-coded, like fierce little study sheets. And then I like to do my studying before I work on the homework, because then I can treat the homework like I learned it. There we are. That's kind of impossible for y'all for this summer class because of how quickly the class moves and how long your problem sets are. If you wait until you feel pretty okay about the content to start the problem set, you are going to be starting the problem set Sunday afternoon or evening, and you will barely finish it by Monday. Like, it seems like the right thing to do because you're like, okay, well, if I know the content better, it'll make me answer the questions better. It's just not going to work. And so the thing that you have to do that's more uncomfortable is to work problems as you are learning them and sit with the discomfort of that. Like, let that help you target what you need to learn and let it be part of your studying process rather than a test of what you have learned. I think that that's going to be like a really critical idea. You are going to learn a lot of reactions by doing them and by working actual problems. Yeah.
So would you say that it would be useful to like, or how would you say that we should like keep track of like the actual like rules and stuff? Because like there's certain things like what like a Grignard like reagent is, etc. Like,
Mm-hmm.
do you think we should make lists of like actual concepts and facts?
So I'm going to get to that with the studying approach. These are just some general tips, but we're going to get there. Yeah, no, you're fine. Now, the big challenge for organic chemistry, full stop, is how can you take in a batch of new reactions and integrate them to where you know it cold and can be able to use it in all the scenarios? Because lecture 5 onwards, we are just teaching you 8 to 12 new reactions every lecture. And you're having to take them all in, integrate them, digest them. And then by the time we get to exam 2, you will have 80 to 90 reactions that you need to know all of them, all of the mechanisms, all of the line reactions, and be able to use them together for synthesis. That sigh is right, whoever sighed. That is the energy of it. So the rate limiting step to your success in organic chemistry at this point is how quickly you can integrate those reactions into your own like mental organization schema. So the thing I will encourage you to do is check in with yourself when you are studying quite often. See what is taking more time than what it like yields. Like, see what is being effective for your time. And don't be afraid to try something new. Even if it's just for a day, try a different way of studying it. Or if it's for a new lecture, like give yourself multiple opportunities to reset and to learn from the information you're getting when you're studying. The thing that I have found is the people who come in with a really rigid way of studying and only want to approach organic chemistry that way often cannot adapt to the pace of this and have a really hard time getting the grade that they want. Whereas the students who I've seen come in, especially even if they've gotten a rough exam 1 score, like I've seen students get a 50 on exam 1 and get an A- in the class. And like the students who did that were students who really pivoted and really like took stock of what was and wasn't working and adjusted. And like I'm also very used to having those study conversations with students. So please come pitch to me your study plan. Tell me what you plan on doing, how much time you're spending. I'll be like, that seems good. I would do this instead, blah, blah, blah. Like, we're all in it together. Last thing is just a metaphor about reactions. So I like to think about all the reactions that you learn as tools that you're storing in the toolbox of your head. And if you are working on a project, do you prefer to have a toolbox that looks like this? Option A or option B? Vote now. B. So part of the challenge too is right now it's just a sea of reactions. And it's like, there's no order. It's all chaos. And so part of what we're doing when we're studying is we need to figure out ways of organizing these reactions and grouping reactions together that are similar in order to have our kind of toolbox tidy. So that when we're like, okay, I need to create an alcohol from an aldehyde, we know, oh, okay, I look in this section of the toolbox. So we'll talk about that as well. But with that, are there any questions before we get into the study method? Are we ready?
Yes.
Are we excited?
Yes.
Woo. Okay, so this is my method for studying reactions, patent pending. And it's not even that groundbreaking of an idea, but I do like to just make it very explicit. So in order to effectively learn reactions for how you are tested on it, you need to study reactions at different levels of detail. So the most detailed level that we can ask is the full mechanism, yes. But if you are only rewriting out mechanisms, like the full thing out, if you are only studying that level, those higher order thinking skills, the synthesis, the creating the box problem, it's probably not going to happen if you are just doing mechanisms. And it's because you're doing like a bottoms up approach of learning. And like, it takes a long time to get the whole base of that pyramid solid to where you could do the higher order thinking. And so my pitch is do the higher order level thinking, even if you're not completely done with the bottom level. Like you need to do from the top down and bottom up, and you'll kind of meet in the middle, and then you'll be fine. So let's do this. We're going to go through this kind of level of reaction details and do some analysis on the hardest reaction that you've seen so far, which is the acetal formation reaction. So If you are a tablet user and writing on the section notes, then get that out, have it with you. We're going to annotate this. If you are a paper user, get your lecture notes out. And if someone could like call out whatever page this reaction is on, I think it might be 59, but like, check me. And we are going to be doing some annotation of this. So I'll give y'all like 30 seconds to get set.
How many reactions would you have?
What?
How many reactions would you have?
Depends on who you ask. Like, there's some reactions that I think of as just a special subset of a main reaction, like a variant of it. But, like, some people would call that a separate reaction. So, in my labeling system, you learned, like, 9 or 10 reactions.
Okay, in a lot though. Like,
A lot. Yes, a lot from going from 0 to 10. That's a lot.
right, but usually it'll be like 7 to 9.
Usually it'll be 8 to 12.
Oh, got it.
Sorry, like that is just it. 56? Okay, work. So, full mechanism, that is what's given to you in lecture. So in lecture, you are given the line reaction, you're given the full curved arrow mechanism. So let's talk about where we go from there. So the next level up in level of detail, that kind of zooms out a little bit, is mechanistic logic. So what we're going to do is we're going to go through each of the substeps, and we're going to try to translate what is happening into English. Because right now, this is a lot of visual information, and visual information is hard to study. Like for a bio class, like vocab, words, you have many strategies to learn words. For Gen Chem class, like algorithmic, like mathematics kind of problems, you have a lot of practice doing that. Most people do not have practice memorizing visual information. So let's go through this, and can someone help me by summarizing what we are doing in this first step? Yeah. Yeah, we're going to protonate the carbonyl. Great. Harder question. Why? Daniel? It's very related to that, but like in the scheme of a reaction, why are we going to be trying to protonate a carbonyl? Like, why couldn't we just have done this without acid and have like ethanol just go and attack the carbonyl?
Oh.
Yeah.
Because it's faster. If you have like a H plus, then isn't that what Logan was going?
Yeah. Like it could happen, but it would be really slow. And so remember when we were talking about reactions, we talked about like a HOMO-LUMO gap of the HOMO of one molecule, LUMO of the other. And this gap in energy between them makes it either harder or easier to do reactions. So if you have a big HOMO-LUMO gap, like these two do, there are two ways that you can make the reaction better. You can lower the energy of the LUMO, and then the gap is smaller. Or you can raise the energy of the HOMO, and the gap is smaller. So which are we doing here? Are we lowering the energy of the LUMO, or are we raising the energy of the HOMO when we protonate carbonyl? No. We're lowering the energy of the LUMO. So let's talk about it. Here, we are making the carbonyl a better electrophile by lowering the energy of the LUMO. And what is the LUMO of this molecule? Pi star CO here. So the reason why we're not raising the energy of the HOMO is because in this reaction here, where like the alcohol is attacking the carbonyl is the electrophile, right? So this is the LUMO in our reaction pair. And then why does protonating it lower the energy of the LUMO?
Because we don't have another number.
So when we protonate it,
Sorry. Because we have an empty p orbital after it?
no. So sorry. We only have an empty p orbital if we have an incomplete octet. Positive charge does not equal empty p orbital. There was something over here. Hmm? You're getting there. So think about our low energy trifecta. What are the things that lower the energy of an orbital? Yeah?
It's like more negative formal charge.
So close. More positive formal charge. Yes. So when we protonate this, we make this oxygen have a positive formal charge. And a positive formal charge is like essentially cranking up electronegativity. And so it's going to lower the pi star CO in energy a lot. It's one of the three factors that lower the energy of an orbital. More positive formal charge, more electronegative, or more, I think, S character? Yeah, I think that was yeah. So that's why it's happening. But do you see already, we're having to think. Like yes, labeling was easy, but this why of why does it happen, we need to know that so we know that when it appears in the future, it's doing a similar kind of strategy. I'm going to come back to it if that's okay. So now that we've protonated this, let's translate this second step into just plain English. How would you describe the second step? Yeah.
The oxygen is attacking the pi star orbital, well, pi star between a C and a.
Work. You have the exact right idea, and like, yes, there are lots of ways we can talk about it. Let's generalize it in our reaction terms. A nucleophile attacking electrophile. So I'm going to say an alcohol nucleophile attacks a carbonyl electrophile. And do you see how that both is really general? Like, it's not getting into the exact orbitals, but it's specific enough to where if I said this to another, like, chemist or another person in the class, they could draw that. Like, they would know what that looks like. And we want to get to where we can, in our summaries, we're summarizing in a way that we could redraw the arrows from this if we were not given anything just from our description. Okay. What's the HOMO of this? Yeah, lone pair and oxygen. And what's our LUMO? Well, we already said pi star CO. Okay. Cool. So the next two steps I'm going to combine into one. I'm going to call this the proton transfer, abbreviated as PT. And the why of this, I'm actually going to come back to in a minute. So let's even move on to the next step. This fourth step, we gave a special name. Does anyone remember what we called this? The lone pair push. She has a good publicist. She is the same publicist as, you remember dividing fractions, keep, change, flip? That's never going to leave you if you heard that before. Lone pair push, she has branding. And I'm actually going to abbreviate LPP, lone pair push. And we're going to lone pair push off water. Now, I think Logan talked pretty well about this in lecture. I would go even further. The lone pair push is the cinematic moment. It is the drama. It is the tea. It is the shade. It is four roommates sharing an apartment, and Chelsea says, "Brenda, get out. I've had it with you," and kicks her out the door. It's drama. It's breaking a sigma bond with carbon. You have only seen sigma bonds be broken for like acid-base things. She is new. She is making change. This is grassroots. So this is what the entire reaction is building towards. Like, everything up here is leading to this step. Big. And we need to think of her that way. We need to appreciate her. So in this step, what is our HOMO-LUMO interaction? It's all in the same molecule. So what's the HOMO? Lone pair and oxygen. Trend alert. Lone pair and oxygen is the HOMO. What's our LUMO? Well, we broke a sigma bond, so we put electrons in the sigma star, the antibond. Amazing. Okay. Lovely. So that's the drama. That's the, like, I need a moment to process. Whoa. In the narrative. But we're not going to pause. So if we back up here, now we start to think about this proton transfer. Why did we do this? In the context of this lone pair push, what did this proton transfer accomplish? Yeah, Aria.
It created a leaving group.
Yes. So this OH right here, if we tried to just do our lone pair push here, she's not going to be a really great leaving group, because if we kick her off, she's negatively charged. Whereas water, when we kick her off, she's neutral. And so in the roommate apartment metaphor, I liken this. This is what names I use? Chelsea and Brenda. This is Chelsea packing Brenda's bags for her right before kicking her out. Like, truly making her a better leaving group. So, yes, one reason that we did this is we need to make the OH a better leaving group, which I'm abbreviating LG. Okay, so that's half of it. And then what's the other half? Why did we deprotonate this other part? Yeah, so this is the girl who's doing the lone pair push. This is Brenda. No, Chelsea. Chelsea kicked out Brenda. So she's doing the lone pair push. If she has a positive formal charge, is she going to want to use her one remaining lone pair to make a double bond and share her electrons further with people? No, not at all. That would put an oxygen with a 2+ charge. It's over. No, like that's never happening. So we need to set up the OET for the lone pair push. And that's how like this part of the reaction fits into setting up for the lone pair push cinematic moment. Okay, then what's going on after that? Anyone, please. We have another nucleophile electrophile attack, right? So, and if we zoom out, whoa, deja vu, right? We have an alcohol nucleophile attacking carbonyl electrophile. The carbonyl has a positive charge yet again. So truly what I'm going to do, I'm going to copy and paste because we know it's the exact same homo-LUMO interactions. And when you're studying, you should be looking for these patterns where like they're using the same mechanistic logic over and over. Okay, our last step here. Then, what are we doing in our final step? Say it one more time. Heard. Just a deprotonation, yeah. Yeah, this talk has more awkward silences if y'all don't participate. So say things even if they're wrong. I appreciate because other people are probably thinking what you are. Yeah.
This might be kind of late in the game to ask, but deprotonation is when you make it more negative, right?
So yes, but like I really think of deprotonation as literally like deprotonation, remove a proton. So like just removing a hydrogen. Yeah, but it takes it from positive to neutral or neutral to negative. Yeah. What was the question over here?
Yes, I was gonna ask if, yes, so basically like for the lone pair push, arrows in step 4, I don't understand the arrows because the lone pair is going to the, to like a
So it is putting electrons in the sigma star,
sigma star.
but when it does that, the sigma star thing just dissolves because she leaves.
Yeah.
And so that becomes a double bond. It becomes the pi bond.
And then what about the other arrow? Oh, the other arrow is just going up to O.
Yeah, so this is just actually kicking off leaving groups. So right now this is one lone pair, but it shows she has 2. So this takes the electrons from that bond, puts on the oxygen.
How would you say that in like molecular orbitals? It's like sigma CO to
Well, so the thing is, when we do our MO diagrams, we're talking about something happening in the moment, but what you're talking about is a before and after. Before, these electrons were a sigma bond. After, these electrons were a lone pair. So we can't really do the same kind of notation the same way. Yeah.
So for the third step, the proton transfer,
Mm-hmm.
being that we're just removing a proton from one side and putting it on the other, why is it that the oxygen from the OH could just attack the hydrogen and then
Like, why couldn't it just do this?
yeah, and then that one?
It's one, because it's unlikely. Like, she essentially would have to like stretch in order to actually do that. It would form like a little 4-membered ring, which is pretty strained. And then secondly, she's in the hustle and bustle of the city, and there's just so much solvent around that's just bumping into it. And so like this bumping into it is just gonna happen faster. Did Logan use sol in lecture as just abbreviation for the solvent or something in the solution? We don't care what it is, we just know something's removing a hydrogen. Well, the last thing here, so why did we do this deprotonation? It's not a trick question. Just to make it neutral, yeah. Okay, so, woof. Like that was a lot. Like we were like very in the weeds of it, but we do need to understand why we are doing this. If you're just drawing an arrow and you don't know why it's happening, then like you are doing yourself a disservice in terms of learning the reaction. Like you are going to need to know why you're doing all of the arrows. And then once we have it all translated into English, I pre-wrote this, but we can make a little nice, cute little list of all of our steps. And y'all are good at memorizing lists. Y'all have memorized lists in the past. I'm probably sure that each of you could list off a list right now. But this translates all of this visual information into a list that you can study using more traditional methods that you've seen before. Yes?
Sorry, in the first step, that hydrogen is from like the H plus on the arrow.
Yeah, from the acid. And there's no like actual just H plus. Typically what we would do is we would have our alcohol and we would add an acid like HCl. These two would be, react with each other, and like you would have ETOH with another plus, and this would go grab one from over here. Either that or it would grab one from HCl directly. Yeah.
So you're saying on the exam we're not allowed to put like the arrow pushing?
No, you are, but for synthesis questions, like the one synthesis question that you have on the last page of the exam, curved arrows give you no points because we can only grade reagents and structures. And I, yes, that's exactly it. Yes. So with this, let's zoom out just a little bit. And we can categorize all of these steps that we did as one of three different types of mechanistic logic at kind of a deeper level. So which of these steps are acid-base steps? 1, protonation. 3, the proton transfer, and deprotonate. And acid-base, like arrows, after lecture 2 and the first P set, we consider that like as like, y'all pretty much have acid-base arrows down. Like they're kind of like a lone pair grabs a hydrogen and then you give the electrons back. If I say like deprotonate an alcohol and close your eyes, like you should have some sort of mental image of that now after doing it a few times on the problem set and lecture and everything. So these are all kind of old arrows. Then a nucleophile attacking a carbonyl electrophile, she's the theme of the party for lecture 3. She is the thing that every reaction in lecture 3 has in common. So that's this second type of mechanistic logic. And the third and final like different one is the lone pair push. But pretty much every reaction that you learned in lecture 3 is just these 3 steps, just in different orders and like different combinations. Like you only have 3 kind of valid moves for your mechanisms. Yeah.
If we're stuck, let's say we forget like a step in this reaction, is it okay to still reason by like closest homo, closest lumo?
Potentially, but it also can like lead you astray. So we're going to talk about more things that are going to help kind of keep you on track with it. Like, yes, we'll come back to it. So we've done now our most detailed levels, full mechanism, mechanistic logic. Let's zoom out even more. So let's study the line reaction. So on a line reaction, you should always do some functional group analysis, and we all have our functional groups memorized now, right? So what functional group do we have here? Aldehyde. So this is the thing. I'm going to do aldehyde / ketone because this could also happen with ketones. It's just this specific one is an aldehyde. Yeah, dig dog. What functional group is this? Alcohol. Then we have an acid catalyst. And what functional group do we have in the product? Acetal. It'd be really messed up if we called this the acetal formation mechanism and we did not form an acetal. That would be really, really rotten. So, remember, I've said it a few times now, we need a shortcut. We need a way of just being able to kind of predict the product without writing the full curved arrow mechanism, because also the mechanism is long and we're likely to make mistakes if we're recalling it, and we want to be able to answer our box problems in a reasonable amount of time. So the strategy that I use, I call it the fake mechanism. The fake mechanism is not rooted in reality. It's very smooth brain. It's drawing instructions. A fake mechanism includes words like erase blank, draw line to blank. Like, it's really just like, how do I draw what the product is? So if I was looking at this reaction and I had to come up with a fake mechanism for myself, these drawing instructions, the first thing I'd say is erase the carbonyl. Okay. And then the second thing I would do is I see I need to have two OETs in its place, right? And this OET is like from the alcohol over here, which generally is the form of ROH. So when I'm kind of generalizing this rule, I'm going to say draw two ORs in its place. So much shorter than the real mechanism. Like real happy-go-lucky. So, with this little example, try out the fake mechanism. Try just drawing the product, given this alcohol and this ketone starting material. Take like 30 seconds.
Wait, is that a hydrate?
So step one, we erased the carbonyl. We just have a naked hexagon. In its place, we put two ORs. And our R group has 1, 2, 3 carbons. So I just do 1, 2, 3, 1, 2, 3. Done. Box problem answered.
Oh, because it's minus the H.
Yeah, because we're just adding the ORs, not the OR and the H. So again, it's just drawing instructions. And then, after you do this, I'm not going to write it out here fully, but what if we want a fake mechanism for doing the reverse, because it's a reversible reaction, right? Then my fake mechanism would be erase the two ORs and then put on a carbonyl. Yeah. So again, you want to be able to move kind of backwards and forwards for these reversible ones really easily, and just these drawing instructions are helpful. Yeah.
I have a question.
Mm-hmm.
Why did you put like the chain for the R? Like, how did you know?
Because this is the alcohol. So like the chain that we put on is based on whatever alcohol. If we put on ethanol, we have OET. If we put on methanol, we have OME. Yeah. Heart. Okay. Yeah.
What if you have to show, like, so, you guys want to ask us to, like, show the steps of, like, the line reaction? Is this, like, product or what?
I mean, line reaction explicitly is don't show the steps. What is the structure? We are only grading the structures. If you write out curved arrow things on the side, it earns no points. Like, we just can't grade that. We can only grade the structures that you give us. And so you just need a system for writing correct structures. So that's kind of the line reaction level. And the warning here, which I know you all are smart, so I shouldn't even put it in. Don't only learn the fake mechanism. You also have to learn the real mechanism. But we use them for different questions. Both of them are useful. Okay. Last thing is thinking at the highest level of the kind of thinking with an eye towards synthesis. What is the purpose of this reaction? And by that, I don't mean like some like loosey-goosey kind of like, what is my life's purpose? Like, why did some postdoc spend 6 years on a project like to make this reaction? Why did we put this reaction in the course? Why are we asking you to learn this? And typically, the purpose of a reaction for organic chemistry is to convert between functional groups. Like that all it really is. Convert between functional groups, connect things or disconnect things. So, in this case, does someone want to take a stab at the purpose of this reaction?
Convert between functional groups.
Okay, but more specific.
Formative.
Yes, yeah, good. And I'm going to add a big keyword here. So the big keyword is reversibly interconvert between a ketone or aldehyde and an acetal. And the reason why up until this point, when we weren't thinking on the big picture level, the reversibility didn't really matter because we're just talking about this reaction. But when we get into the scheme of like trying to build molecules, we want to know the fact that, hey, if we have a carbonyl, we could just turn it into an acetal for a little bit and do other things and then put it back. We could protect the carbonyl, which is kind of what Logan tried to do in the last 5 minutes, but it was really quick. I think he'll readdress it later, and it'll be in the exam review. Don't worry. So, reversibly interconvert between a ketone aldehyde and an acetal. That's why we have this. This is why, the same way a hammer, the purpose is to hammer a nail. The purpose of this reaction is to reversibly blah, blah. Okay, so purpose is one. Second big picture thing, what are the goals of this reaction? And I think of goals like those like SMART goals, like achievable, blah, blah, blah. They are literally what bonds were made, what bonds were broken. So, what's a goal of this reaction? Break. And you're talking about with that carbonyl, right? The single bond or the double bond or both? So, to answer that question, actually, we have to think a little bit more. So this oxygen here, is this one of the oxygens in the products? No, but the only reason we actually know that is from the real mechanism. Like this oxygen, we protonated her, she becomes this OH, then we protonated her, she became an OH2, then she left. So she's gone. She was not renewed for season 3. She was kicked off the island. So we need to break the sigma CO and pi CO. So that's our break goal. And then what bonds do we need to make? Yeah. So I'm going to number this list. 1, 2. So we need to make 2 bonds to the OR. And these are like sigma COs. Okay. So now that we have this goal in mind, let's take one more look at the mechanism. I promise we won't do another full mechanism sweep again. This first step, did it accomplish either one of our goals? Or was it a setup step? Setup step. Second step, did it accomplish either one of our goals? Yeah, what did it do? You're great. So it broke the pi CO, and it made one of our 2 OR sigma COs. So we got like halfway there on both of our goals in this one step. So yes, it makes sense why they would invest so much time in this step to set it up to do this. Half of our goals are done. Step 3, did we accomplish any of our goals? Or was it a setup step? Setup step. Step 4, did we accomplish any of our goals? Yes. Yeah. We broke our sigma CO because remember, this was the carbonyl originally. So over here in this step, we broke that pi bond. Now we're going to break the sigma bond. Great. So that means that after this step, our first goal is complete. We have broken both of the bonds that we need to. Okay. Step 5, do we finish our goals? Do we do our last making? We do. So we do make 1 OR sigma CO. So I think this framing of like, we have an agenda. We are coming in with a plan for this reaction. we are trying to accomplish these specific concrete chemical goals of making and breaking bonds, it is a helpful framing for the mechanism, for why we are doing each of the steps. And also, do you see, by doing this and by doing all these levels, we've actually thought a lot about this. Like, would you say that you understand this reaction more than yesterday in lecture? Yeah, because we've spent more time, we've been asking these questions. And this kind of scrutiny for the reaction, it is going to be your job to do this kind of process for all of the reactions to get to where you understand it at this level. Last thing before I like finish off this little section. So the last thing in the big picture is just generalizing, because we often give you it in terms of like just a specific reaction with specific molecules. Let's generalize it with some R's. So this I'm going to indicate as a ketone or aldehyde. So it has like some carbon thing on one side, on the other side either a carbon or a hydrogen. Then we're going to do an alcohol, and I'm going to call this R prime just because we already have a lot of R's in the mix. And then we have H plus acid, and we are going to make our general acetal. Cool. So if whatever you're doing to study, I'm not saying that you have to do this method. This is just the method that I wound up doing, and very much not in an intentional way. Just in second semester of OCHEN 2, when I started doing better, I was doing this. And then I like thought about it after the fact, and I was like, what was I doing? So as long as whatever way you are studying reaction engages with these levels of details of the mechanistic level, the line reaction level, and like this bigger picture purpose, like synthesis level, you're going to be set. So you are going to need to do some sort of studying for all the reactions, but to help you out, on the last page of the section notes, I made a reaction summary sheet. So this goes through all of the reactions from lecture, and like, for example, the acetal reaction, these are the sub-steps that we just did. This is the generalized kind of line reaction that we have here. And I also am putting like notes from the lecture notes that are things to kind of watch out for, variants. Like if you use a diol, like both of your alcohols are connected to each other, then it forms these little cyclic acetals that are like little rings of just like a special note to watch out for. Or like this one, if you carry it out at 0 degrees versus 80 degrees, it does different things for reacting with enones. Like I tried to kind of show you, if I was studying for this test for the reactions, what is the review sheet I would make? And because I've had 7 years to make it, it is like typeset and like yassified. But your study materials, make them functional. Don't like waste time like making it look nice. Oh, this is a trap. So if you take this like review sheet and you use it and do it with all the problem set 2 questions, you're going to do great. You're going to answer the questions. You'll be able to find all the information really easily. But then when you get to the exam where you do not have my review sheet, it will be rough. So you still need to do the process that we did for like understanding these reactions and really analyzing and go through in your studying. So it is a trap. Make sure you are also still doing the studying. I would say create your own like study sheet and use this as a template. I just wanted you to have like some sort of scaffold to kind of base it off of. But with that, this has already been a lot. Let's take like a 2-minute break, and then we're going to regroup, and we're going to come back and talk about some of the reaction families outside of the acetal stuff. So, yeah.
Can you say make your own review sheet and what's that look like?
Literally like what I did. Like make your own version of this, not copying my notes, but going through lecture and like analyzing the reactions on your own and building it, and then compare yours with mine. Is there stuff I left out? Is there stuff that you left out? Like, yeah.
Your review sheet, should it be like this, like with this little section for each reaction, or should it be like this entire, like all the levels of detail for the reaction?
I think, so the levels of detail to me is the process of studying. It's not a review sheet.
Oh, I see.
Review sheet to me is like, okay, I've done my process. What are the things I've learned? What is like the kind of recap of it? She's not the episode of The Bachelorette. She's the recap podcast. Yeah. Why? Okay, if I didn't talk the way I talked about it, it would be unbelievably boring.
No, it's everything, to be honest.
Yeah, like, and the only way I don't really actually like chemistry. I like making little stories.
Oh, that's what you meant.
Oh my god, that's
It's the truth. Wow.
Yeah.
Mm.
And I was trying to
Oh, sorry.
I'm gonna try to fix the grapes.
Work. And yes, if you could do that like before 5 o'clock, because that's when I'm gonna start trying to do the grading. Yes. So, like, it literally won't even let me upload it because it says you don't exist. Wow.
I didn't.
yeah, I have a sister and me and my partner. I do that, so yeah, it'll, I mean, it could save you time, but it's not. It's already doing it anyway.
Okay. Work. For piece at 2. I don't see it yet, but I'll check after. Yeah. Yes, definitely. And actually, this course, one thing that's different is because we do synthesis in it and like the fall 17 doesn't, it's actually a good course to set you up if you want to do 27 or if you want to do 30. So like if you get into the class and by the end of it, you're actually like, hey, this synthesis stuff is actually kind of interesting, you could go into Chem 30 instead of 27. Or you could do both because Chem 30 and 27 cover entirely different content. So, but, okay. Work. Sorry, I saw someone explaining the difference between 17 and S17 and 27 very well. I was like, slime. So, remember how I was talking about organizing the toolbox earlier, where we want to have our little compartments for our different reactions? Well, my kind of way of doing that is thinking in terms of reaction families. So these are reactions that share very similar mechanisms or share similar purposes. So like, for example, the acetal reaction was in this kind of big family, which are called the reversible carbonyl additions, or which I'm calling them that. They don't have like an official name. And again, the purpose of all of the reactions is to reversibly interconvert between some sort of carbonyl and some other functional group. And all of them use similar steps. Like the acetal one is longer than the others, but all of them have the same like acid-base, nucleophile attacking carbonyl, or lone pair push steps. Like they're all doing the same chemistry. The other two families here are the hydride equivalent reactions. These are the reactions where the purpose is to convert a ketone or aldehyde to an alcohol. And then the organometallic reactions, or the carbanion reactions. These, the purpose of it is to add an alkyl group to a carbonyl. And it just helps us group several of the reactions together that function very similarly or that have similar mechanisms. So with that, for the rest of our time today, I'd like to zoom in to these two families a little bit and talk, give like an intro to it. So we just said the purpose is to add an alkyl group to a carbonyl. But when we do that, we are often going to create an alcohol. The purpose of the reaction is not really to generate an alcohol, because we have other ways of making alcohol. The thing that's special that it's doing is we are adding an alkyl group. Now, in this entire course, you are only going to learn 3 or 4 different ways to make carbon-carbon bonds. So if you, on the first exam, have to make a carbon-carbon bond, you have used a reaction in this family. So, again, there are very few strategies. It's a big deal to make carbon-carbon bonds in organic chemistry. So, oh, I love the meme here of the dog playing with the little doggos, and it's like the carbonyl and the alkyl group, and it's like, kiss. And it's literally like, if you're using the model kit, it's literally, you just plug it in, like you're building the Legos. So, why don't we just use deprotonated alkanes to do this? Well, what's the pKa of alkanes? Girls, it's on the test. The pKa of alkane of methane. 50. There we go. It's on the list. It's one of the things we're memorizing. I'll assume that you were memorizing the functional groups, and so you're going to do the pKs in a bit. Yeah. Okay, so pK of 50. This is the type of reaction where you're like chatting with someone and you're like, oh, did you hear about the explosion in lab the other day? Like, this thing is crazy. You need a base strong enough to deprotonate an alkane. Things are going to explode. Like, she probably can't be exposed to the air. So we need something that's going to react like this, but isn't as crazy as this. And so what we need, this we call a carbanion. We need something that's a carbanion equivalent, something that's kind of going to react like it. Now, normally when we see carbon in bonds with things, like carbon-oxygen bond, who's more electronegative here? Oxygen. So we'd have a partial negative, partial positive, right? But we need carbon to behave almost like an anion. So we need to have a dynamic, a bond here, where carbon has the more electronegative, or where carbon is more electronegative, words. So carbon has electronegativity of 2.55, and to get it to be the more electronegative element, what we are going to do is we're going to create a carbon bond with a metal of some sort. And metals typically have electronegativities of less than 2. So the metals that we use are magnesium with bromine, lithium, or copper. And when we have this carbon metal bond, carbon's more electronegative, so we have the partial minus over here, partial plus on the middle, and it's going to react like a carbanion. Now, I say like, we never want you to draw a negative charge on a carbon here, like for this reaction. We want you to draw this bond. We want our arrows to start from that bond. But this is kind of like what it's acting like. So we have two main players. We have the Grignard reaction and organolithium reaction. So the Grignard reaction is whatever our group that we're trying to add is, RMGBr, with diethyl ether, Et2O. And we have two steps here. The first step where we add our Grignard in our solvent, and the second step we do an acid workup. Let's talk a little bit more about that. So Et2O, our solvent, she is literally just a medium for the reaction to take place in. So this carbonyl on its own, it's going to be some sort of oil. This, our Grignard reagent, is going to be a solid. So if we didn't have our diethyl ether, it'd be like trying to get an oil to react with a solid. It's not going to mix well. It's going to take forever. And so that's why we need something for it to take place in. And typically we want solvents that aren't going to really butt into the reaction unless we need them to. So ethers are typically not that reactive. And so it is just a good liquid medium for the reaction to take place in. Now, diethyl ether, it's literally like two ethyls on an oxygen, and then the carbons on either side make it an ether. So I think of it as an auction bat. It kind of looks cute. You can give it a little like, boom, boom. Sure. Anyway, but it looks like a little auction bat, and Grignard sounds like the name of a vampire. So that's how I remembered it. Here we are. I know. Grignard sounds like a vampire name. Yeah. Now, the main solvents that you are going to see, especially for lecture 3, you've only seen two types. You've seen either ether as a solvent, in which case she does not participate in the reaction, or you've seen alcohols as a solvent. And there are certain reactions that we want alcohols as a solvent, and we're going to get back to that later. But for now, we want something just neutral for it to take place in. The second thing I want to note is this like acid workup here. So in some classes, they make you write a specific thing. They make you write H2SO4 or HCl. Sometimes you can even quench a reaction, stop a reaction, by adding water to it, and that could be your acid workup. For the purposes of our class, we do not care. So you're just going to write H plus workup. But if you're looking at outside resources, then you might see H2SO4 for the second step. I don't want you to be confused. It also is going to be very important that we number these 1 and 2. If you do not include this, that's minus a point. Because without those numbers, you were saying all of this goes in the beaker at the same time. And if all of it went into the beaker at the same time, we would not get the reaction we want. We'll come back to that in a second. So how do we make these organometallic reagents? We start with alkyl halides. So if we have an alkyl halide, what we can do is we can add elemental magnesium. That's what this O means. It just means like solid magnesium as opposed to like magnesium 2 plus the ion. Okay, so solid magnesium diethyl ether, that magnesium will just slip in there. and you don't have a mechanism for this. You are not responsible for any mechanisms because metals are kind of beyond your pay grade. You're here for carbon and like main group stuff. Then the other version is if you add 2 equivalents of lithium and Et2O, you'll make alkyl lithium from the alkyl halide. So one big thing, the only reactions that you know for exam 1 that start with an alkyl halide are these. So if you ever are in a situation where the only thing that you can react with is an alkyl halide, you have to turn it into one of these. And again, you don't need to know the mechanism. Now, one thing about the Grignard reagent, it's also true of alkyl lithium here, is they are really strong bases. So, like in Georgia, trying to do the Grignard reaction is a pain in the butt. Because if it's even a little bit too humid in the air, the Grignard reagent will react with the water in the air over your carbonyl compound. Like, it's on the scale of like parts per million. If there is water, it's going to disrupt your reaction. It's horrible. So, what happens, and this is like an unwanted side reaction to be so clear. If we have water, the Grignard, instead of attacking the carbonyl, is going to go and grab this hydrogen and break the bond. And then we will have just added a hydrogen to the R group, and then we have OH minus. Did this accomplish our goal of adding an R group to a carbonyl? No. So, like, this is an unwanted side reaction. And I think Logan introduced that in lecture yesterday, but I saw several people confused by that, of, like, writing it out, because it's like, I don't know. I think this cautionary tale, you were like, oh, this is a reaction that adds a hydrogen. And I was like, that's not the important part. So the actual mechanism of it, compared to acetal, easy, breezy, beautiful. Acetal, I don't know. So you go from the sigma bond between the carbon and the metal, attack the carbonyl, push up to the oxygen. Then, in the second step, all you do is protonate it with the acid workup. And you're done. 2 steps. So cute, so quaint. One thing I did not really harp on when we were studying reactions, your arrows need to be deathly specific. If I drew this separately, like if I instead drew this as an arrow that was like bon from the R, that does not earn points. If I drew it from the metal, that does not earn points. If I drew this to the double bond, that does not earn points. If I ambiguously drew it to the carbon, no, that's actually pretty, see, it's hard to do it bad now because I've been trained into it, but you have to be so specific as to which bond or atom it's starting and ending at. Because when you're doing a curved arrow mechanism, you're proposing an argument for how the molecules are behaving. So it is really specific, and I just wanted to say that note. So, okay, we have these 2 reactions. Let's talk about one variant of it, which is, what if instead of ketones or aldehydes, we react with an ester? So, when we have an ester in either one of these reagents, the organolithium Grignard, we are actually going to add our R group twice to the carbonyl carbon. So the kind of automatic response that I want you to have when you think about or hear of an ester in the context of exam 1 things is double addition to esters. So can we try our Pavlovian conditioning? So I'm going to say ester, and you say double addition to ester. Yeah, okay. Esther. I have a matcha latte ready for Esther. You should be having dreams where there's a character named Esther, and then she says, hi, my name's Esther, and in the dream you say, double addition to Esther, and she asks, what does that mean? And you say, I don't know. Like, it needs to haunt you, it needs to be automatic, subconscious. So let's talk about why we do the double addition to esters. So the same step, first step, exactly the same arrows, everything. But then when we get to this intermediate, she is different. So earlier, when we had this intermediate, we had an O minus here. And then we only had like carbons or hydrogens, like carbon-carbon, carbon-hydrogen bonds. And carbon-carbon bonds are hard to break. Same with carbon-hydrogen bonds. But carbon-oxygen bonds are easier to break. They are, yes, amazing. Yes, MO theory. They're higher up in energy. They're easier to go. So you can do a lone pair push down and kick off OAT. Bye, Brenda. And now, what we're left with, what functional group did we form? You have to say it. A ketone. And we are still in this step of the reaction, and we created a ketone. Grignards react with ketones, and so it's going to go and react again, a second equivalent here. And then you do your acid workup step, and it's neutralized. But the reason why esters do double addition is because they have a built-in leaving group, whereas ketones and aldehydes don't. Questions about her? Yeah.
So in the first step, there are two sub-steps, which are first to, basically, we want to first give the double bonded oxygen, the lone pairs, like the materials, to be able to kick off the leaving group.
Yes, but also like literally the goal of the reaction is to make two R groups added. This is adding one of them, and it just so happens here, once we've added one, we're set up for a lone pair push. Whereas like for the other ones, we aren't.
And could you please remind me the difference between an R group and when we just write X? In the functional group, like X.
So R is just shorthand for some alkyl group. Like it could be CH3, CH2, it could be a phenyl, it could be like some like hydrocarbon thing. We don't care what it is. Yeah, all right.
Could you please explain, what for the reagents, why it's 1, 2, and then 1, 2 again? Like why it's what?
Oh, sorry. This is options. You could use either one of these. Like this is just like I was like trying to make it look cute, but it's like you could just use this top one, or you could just do the bottom
So
bridge.
essentially the R-MGBR and R-Li are the two Grignards.
Yeah.
We should-
Or Grignard and organolithium. But yes, so you're getting at really what the next thing we're going to talk about is. So up until this point, these reactions appear identical. So why did we teach you two when one would do? And the difference comes from when we react with enones. So enones are one of our compound functional groups. We have an alkene and a ketone. And when we have an alkene and a ketone next to each other, these double bonds all have p orbitals. So what do we have between all of these atoms? Resonance, delocalization. Very good, very good. So because we have resonance, this thing is going to react as one unit. And whereas our carbonyl only has one electrophilic site at the base of a carbonyl, an enone actually is going to have a second electrophilic site. So we use kind of an idiosyncratic little system here of we start numbering from the oxygen 1, 2, 3, 4. And we say if we add at the base of the carbonyl, that's a 1,2 addition. And then if we add at the very end of the alkene, it's a 1,4 addition, also called a conjugate addition. So the other thing, Logan did not use these in lecture, but I have seen this in like MCAT prep materials, and so I want you to just have it on your radar. We're never going to talk about it again. We won't test you on it. But nucleophiles that add 1, 2 only are often referred to as hard nucleophiles, whereas nucleophiles that add 1, 4 only are called soft nucleophiles. And it's just, again, like a history thing. So let's look at our organometallic reactions when it comes to enones. So if we did our Grignard, so we have our R-MGBR ET2O and an H+ workup, the Grignard reaction is unselective for enones. We are going to get 1,2 addition of our R group and 1,4 addition. Now, if we are doing a synthesis and we're trying to make a specific product, do you think we want unselective reactions? No. So Grignard, she's fine and dandy for simple ketones aldehydes, but for enones, we don't use her. Okay. Well, then let's say we only wanted the 1,2 product, then we would use our alkylithium. So the alkylithium is a hard nucleophile. But then we have an issue, because what if we want to create only the 1,4 product? We need something new. So there's a third girl entering in late in season 2 here, but she is the drama. She is the sensation. We have the organocuprate reaction, or the Gilman reaction. So there are two ways to write the reagents for this. I'm going to show both of you, and I'm going to tell you which one I prefer. So the first one is your alkylithium, and you're going to sprinkle in copper bromine with ET2O as our solvent with an acid workup. That's one way of writing it. I think that's the first way Logan introduced it. But you can also just rewrite this as R2CuLi. This is going to be the preferred way to put it. Mostly because it simplifies steps and because it is what all of the answer keys use. So I think it'll just be easier for you if you do it this way. Basically, when you have organolithium and you add a copper bromine into a mixture together, they are going to form this complex where two of the R groups are going to associate with the copper. Copper will have a negative charge, lithium has positive. We'll never ask you to draw this, so you don't need to worry about that structure, but you just need to be able to draw it this way. So for example, if we wanted to add a methyl 1,4, we would use methyl 2CuLi. If we wanted to add a phenyl group, PH2CuLi. But we can also do it with more complicated things. So I want you to take a minute and think, what reagent would I use to add this thing, 1,4? So we're going to use some sort of Gilman copper, but how would you write that? It's not an ethyl. It's not even a dimethyl. How many carbons is she? 1, 2, 3. So it's some version of a propyl, but if we just said propyl, then it's going to look like we're adding it this way. Isopropyl. But even with isopropyl, sorry, I didn't mean to gaslight you. Yeah. So the way that we can draw it, and I want you to see this because we can do it with even more uncommon things. We are going to do our isopropyl, but we're going to draw parentheses around the 3 carbons that are added, and we'll do our subscript 2 there, and then CuLi. Because it forms this complex with 2 R groups, R2CuLi. So that's how you add a more complicated thing with a Gilman. Now, the Gilman reaction, Logan put a rough mechanism of it in class. You are not responsible for a Gilman mechanism, mostly because the actual mechanism is a little bit beyond y'all's pay grade right now. It involves the copper doing a complex with the carbonyl, which y'all have not seen. So no mechanism. The other thing to know about her is copper is actually more mild than the lithium or magnesium. And so it's going to be less reactive than the Grignard. It is not going to react with plain Jane ketones, aldehydes. It's not going to react with esters. It only does 1,4 with enones. Yeah.
How are you supposed to know which one of these you're supposed to use? Is it just
It's about what you want. So if we are doing, for example, in the problem that we're going to see, if we are trying to figure out how do we go from this enone to this product, we need to see, we added something 1,2, we added something 1,4. Okay, for the 1,2 thing, we need to use lithium. For the 1,4 thing, we use copper. So it's about using it for whatever purposes you're going to see. Again, this is where I kind of like that there is a degree of agency in synthesis of you get to choose what happens to make this work. I think that it's a much more active form of participation than a class where you're memorizing a bunch of facts and then have multiple choice questions over said facts. But one last thing before we go over to the practice. So we do want to learn the mechanism for conjugate 1,4 addition. And the example that was given in class is thiolate addition. This is the only reaction that I didn't put on the summary sheet just because I don't know why. I just didn't. It's because it doesn't exactly fit. It's not a carbanion. It's not a hydride. It's not a reversible thing. So here we are. So we have a thiolate here, and a thiolate is just the negatively charged version of a thiol, normally with an SH. And 1,4 addition, we are going to add at this far carbon, the 4 position. But then this is where it's a little bit different. We are going to push in this double bond, make another double bond, and push up all the way to oxygen. And when we do that, it's kind of combining some resonance arrows with a nucleophile electrophile arrow. Without this could lead to a resonance structure. So when we are doing it all together, we are saying, hey, these molecules are coming together and there's some resonance going on. Yeah.
Can I just clarify for the arrow that's going from the alkene up?
Mm-hmm.
Is it going to the bond?
It's going to the bond.
Single bond.
Mm-hmm.
So what
So the donor acceptor orbitals, you would have a lone pair on sulfur going into the pi star CC. Then you would have the pi CC going into the pi star CO because you're breaking the pi CO. Or pi, yeah. You are breaking this bond, so you're putting electrons into the antibonding orbital.
Oh, so those two arrows are just encompassed by that one pi CC to pi star C.
Yes. Mm-hmm. Yeah, totally. So the product that you wind up with looks like this. And we are pretty close to our product. We know that to get to the product, we're going to have to make the double bond with oxygen, right? But then there's something sneaky going on. So let's play detective. Do you think this carbon is the same as this carbon here? Like those look to be the same, right? Well, no, they are the same carbon. But in the product, how many hydrogens are on the carbon? There are 2. In the intermediate, how many hydrogens are on it? 1. So the sneaky thing is another hydrogen was added here, but it wasn't immediately apparent before we did our detective work because we imply the hydrogens. So have the detective glasses ready. So what we are going to do is we are going to push down, reform our double bond, and then we are going to go and grab a hydrogen. I don't know why. It wasn't even you. It was your reaction that made me giggly.
So funny. No, actually it is.
Here we are. So,
This is probably
so we are pushing down, forming the carbonyl. Then the double bond's going to go and grab the hydrogen and put it on that far carbon. And Logan didn't use this term yet, but I'm actually going to give this step a name because it's kind of a different, it's not one of our mechanistic logics we've seen so far. It's not a lone pair push. It's not a acid-base step that we've seen before. It's not a nucleophile attacking an electrophile. So this is fundamentally an acid-base step though, right? Like the only thing that's transferring between molecules is a hydrogen. So this is a special type of protonation called an alpha protonation. And we are going to see these again in lecture 5, and he'll like use that name in lecture 5. That's why I'm introducing it here, just to like, you'll see it. And it's because we call the position to the left and right of a carbonyl the alpha position. And then position 2 away is the beta position, then the gamma, then the delta. Yeah. But that's this mechanism. So, practice. I have some questions I've gathered from skill builders, and also this one is one that I just wrote that I think is going to be good practice. I'm going to give you like truly 2 minutes, 2 or 3 minutes to try to work 1 or 2 of these. I don't expect you to get through all of them, and then we'll go through the rest of them together as a group. So the first one, you're going to be doing just a basic mechanism. This one should just be like regurgitation of the arrows from like the when it's introduced. Then you have some box problems to try. Yeah. Was there a question over here? Work. Simran, I love your shirt. No.
Why are you laughing?
Work on your problems. Sorry. Work. First letter. Micah. Rose. Ahmed. Work. Nate. Alyssa. Simran. Evie. Asias. Work. Sue. Summer. Nora. I know the first letter. Thank you. Lavinia?
Yes.
Work. Daniel. Fabian. Aria. Gia. First letter, just the first letter. S. You're not Sophia. The first letter might be what? Okay, shh. I'm so sorry. I'm gonna get there. I find shame a powerful motivator. So next time that I don't get it, be offended. Be like, really? Really? It is. Wow. Yeah.
Where does the MG go?
She just falls off. Like, because the electrons that were in this carbon magnesium bond keeping them together, the ethyl was like, I'm taking the children and I'm marrying someone else. And then the MGBR just has no bond.
How do we know that the MGBR doesn't say that we're keeping children and relating?
Because she's less electronegative. She doesn't have custody. Like, the courts will decide in favor of the more electronegative parent. It's a messed up system, but it's the one we live in. And so the MGBR just, like, falls off. Work.
I've always kind of been confused about when we have a sigma bond going to either like a non-bonding orbital or like a astro or sigma star. What atoms connected from that original sigma bond come with it?
This is the only reaction that you've seen where a sigma bond does the attacking. So,
The ones with like BHHH.
oh, it's this one and that one, which is like literally the next page. Yeah. So in those, it always goes with the more electronegative element. Like that's the rule. Yeah. So we're going to talk about this. I know you have not had a chance to do all of them, but maybe you've had a chance to try one or two. The first one, it's just straight up the mechanism. I don't know what more to say about her. Like the sigma bond goes and attacks the carbonyl, pushes up, then this grabs a hydrogen. Did this feel pretty straightforward? Cool. Okay, box problem. So here we have an ester. So what's the first thing that we should think? We're going to try that again. So here we have an ester. So what's the first thing that we should think? Thank you. So in our product, do you see two of something that has been added? The alcohol, we don't have two of. So what do we have two of in the product? We have two methyls. And those methyls were not here before, right? So we're doing double addition of a methyl. We could use Grignard or lithium. I'm just going to use Grignard. So methyl, MGBR, ET2O. And if you want to be that girl, one thing that you can write is two equivalents. That's just letting me know that you're letting me know that you know that that's reacting twice, double addition. You don't have to include it. Like, we are not going to count off if you don't include it, but it's kind of like, yeah, I know it's double addition. If not, like, I'll know what you mean, but, like, again. So, and then second step, acid workup. So that's it for this one. Now, the next one, we talked about a minute, or just very briefly. We added things at the 1,2 position, and we added at the 1,4 position. So what carbon, like, alkyl group did we add at 1,2? What alkyl group did we add at the 1,2 position? An ethyl. What alkyl group did we add at the 1,4 position? Phenyl, yeah. And then remember, 1,2, what metal should we use? Lithium. And then 1,4, what metal should we use? Copper. So now the big question is, did we do the 1,2 addition first, or did we do the 1,4 addition first? And you're going to vote. We are going live. So if you think you did 1,2 first, you're going to do a If you think that 1,4 happened first, you're going to do a So 1,2 addition, 1,4 addition, which one happened first? Do your poses. This is 1,4 addition. This is 1,2 addition. Which one do you think happened first? I'm seeing a lot of 1,2s. I'm seeing very few 1,4s. So let's try 1,2. Let's see what happens. So if we add ethyl lithium with ET2O and H plus workup, then our product after that is this. Now, at this point, do we have a carbonyl in this intermediate? No. Do we have an enone anymore? No, we have an alcohol and an alkene. Do we know any reactions of alcohols or alkenes? I'm so sorry. Dead in the water. So, what we are going to do is we are going to drag these down to steps 3 and 4, and we're going to do our copper 1,4 addition first. So we're going to do pH2CuLi and diethyl ether. H plus workup. And then after that, we're doing our steps 1 and 2 here, steps 3 and 4 over here. Then we would do our lithium, and that would get us to our product. And then the last one here, this one I think is the hardest one, but I'll try to be quick. What functional groups do we have over here? Who is she? What functional group? The circled one, yeah. An ether, thank you. People were saying the alkyl halide. What else do we have? Arene ring, good. Do we know any reactions of ethers? No. Do we know any reactions of arenes? Alkyl halide, do we know any reactions? Yes. The only thing an alkyl halide could do is it could turn into a Grignard or turn into alkyl lithium. So let's just turn it into a Grignard. So if we do that, what it looks like is we still have our OMe, but now she's an MgBr. And the Grignard reaction normally has the Grignard reagent, which is this, reacting with what functional groups? Grignards attack what functional group? Carbonyls, like ketones, aldehydes, esters. This is not a trick question. So let's look at our product here. We have all of this. That's the same. And then this appears to be new, right? We have a carbon here that has 2 hydrogens, but it's an alcohol. And hey, alcohols are the product of a Grignard reaction, right? Well, we need to get the version of this that has 2 hydrogens and a carbon, but is a carbonyl. So this is a molecule we straight up have to supply. We have to write this on the line reaction. And it feels really weird. The reason it feels weird is we're used to seeing carbonyl over here, Grignard over here. And this does the reverse. It has this thing on the left being our Grignard reagent, and then the thing that's attacking the carbonyl on the arrow. And this whole question is here just to show you that that is okay. The last step is just an acid workup. I wanted to do a 5-minute introduction to hydrides, but I'm already 3 minutes over, so I'm not going to do that. It's going to be in the video of the other section recording, because I normally post the 10 a.m. ones. Normally 8 a.m. is warm up, 10 a.m. is good, and then normally by noon I'm tired, but y'all are a lively bunch. Unless I ask you directly a question about chemistry, then crickets. So the thing I will want you to pay attention to, though, is we have 2 different versions of doing this hydride reaction, and they're characterized in different ways. So be looking at this chart to compare and contrast them, and then maybe watch the last 5 minutes of the other video, okay? Thank you for coming to section. Scary announcement out tonight. Let me know if you have any questions. I'll see you tomorrow.